Hello everyone, and this is the second video on the last chapter, okay? Central limit theorem. So a little bit of announcement here. We have 2 lessons left, okay, in my plan. So in the next lesson 43 is central limit theorem, right? And in lesson 42, we talk about the law of large number. And in lesson 44, there will be the surprise. Maybe it's not a surprise because you have seen the surprise before, right? So in lesson 44, we are going to do some coding, okay? Some coding in Python, okay? So you're going to see some numerical example. But in lesson 45, we are going to have the farewell party, okay? Because it's gonna be the last lesson in the course, okay? So if you don't want to miss this stuff, so stay tuned, okay? So stay tuned, please subscribe to our channel, okay? Deconstruct channel. Okay, so that's enough for selling, okay? So in this lesson, we talk about the central limit theorem. As I've said, let's say in the last chapter, that central limit theorem is the most fundamental theorem in statistics. Okay, so if you study the mathematical statistics, this will be one of the first theorem that came up. Even though because we are in probability theory course, right? So this one will be the last, but it's important is not inferior to many of important theorems that we have talked about it before. Okay, so we talk about the sample mean of the large random sample with mean mu and finite variance sigma square has approximately normal distribution with mean mu and variance sigma square over n. Okay, that's why central limit theorem justify the use of the normal distribution as a model for many random variables that can be thought of as being made up of many independent parts. Okay, so everything convert to normal. That's why we have to learn the normal, even though its indication is not in the conform solution. Okay, and then we are introduce the delta method that we are going to see later. Okay, so let's look at this statement, the central limit theorem. Central limit theorem. So there are many versions of central limit theorem. In the textbook, we have two versions, but this version is, let's say, the most fundamental one. In another version is a little bit more complex, but I think we do not use it. I personally do not use it at all. But this version is version that we usually use, okay? So if the random variable expand up to Hn form a random sample of size n, form a given distribution, okay? So any distribution is fine, okay? Any distribution is fine. It doesn't say that it's going to be normal, but just that, okay, mean mu variance sigma square n is going to be finite, okay? Then for each fixed number x, the probability that Xn bar minus mu over sigma over square root n less than or equal to x, this one will converge what? Because we have n, right? As n go to infinity, it converges to the normal CDF. It is normal CDF. Okay? That's why we use the normal distribution in many hypotheses, let's say almost all hypothesis testing. Okay? But why? It seems like the magic, right? It seems like the magic. Oh my God, what does it happen here? But let me show you some magic. The scene behind the magic. Okay, the proof is very long, but bear with me. I am trying not to make it very boring. Okay, but after you have seen the proof, I think that you have the grasp of what the theorem is looking for. Okay, so define yi and this. So this page is the define random variable for simplification. So we define for just the sake of simplification. Nothing interesting here. But what is interesting is this. We have talked about the convergence, right? So Cn converge, that is the goal. Okay, the goal is that Cn converges in distribution to a random variable having the standard normal distribution. That is the goal. But we are going to do it because this one, right? Cn converge to normal. But we can show that using the MTF. The what? The MTF, right? Moment generating function. So the moment generating function is the key behind the magic to simplify this proof. Okay? So you must show that the MTF of Cn converges to MTF of the standard normal. So this simplifies from the probability problem into the algebra problem that we are more familiar to solve. Okay, but I'm not going to show you the full step, okay, but just outline of step to show you what happens. So this the MTF is the what? The MTF of T over square root n over the n. So MTF, be any MTF, it doesn't have to be the normal. That's why I need note with little sign here. But with two restrictions. First restriction is that sign derivative sign at 0, it must be 0. That means the mean is 0. And the variance is 1 because this step is called the normalization. Normalization into mean 0 and standard deviation of 1. Okay, but it can be any MTF. Okay, and this is the next step. By Taylor series approximation, as because it is holomorphic, right? So it is a technical term that if you expand the Taylor series, so if it is getting closer to 0, is this function is close to psi t, but not always, but most functions are. Okay, it has this following form, but doesn't matter about that detail. That detail is in the Leo analysis. Okay, the Leo analysis and the complex analysis. But here we just want you to see the magic, but not require you to do the magic by yourself because it's kind of complex, especially if you don't experience the real analysis before. Okay, so it has this following form. Okay, sign, and we could simplify this. We could simplify this and this because we have some restriction here, right? And this is what we get. Okay, and from this one is another magic. It requires some lemma of the algebra that we didn't go here. If you want to know, you go into the textbook. It's gonna be somewhat complicated. It's gonna be somewhat complicated, but finally, you could get this one. From the MTF, we simplify first step using MTF, simplify next step using the Taylor, and then we use the weird algebra stuff that we didn't talk here. And we say that as n go to infinity, the MTF go to the normal. As n go to the infinity, the MTF go to the normal. That's all. That's the magic behind the central limit theorem, and I have walked you through the magic. Okay, but not the full magic, but I think you have seen outline, the detail outline. Okay, but for the detail, I think you have to look in the textbook because it is somewhat complicated, especially the algebra here. You have to put some lemma, okay, before proving this. Okay, and that's all. That's all about the central limit theorem. Okay, so let's define the convergence in distribution clearly. Okay, So let x1 up to x2 and so on be a sequence of random variables for n equal to 1, 2, and so on. Let fn denote the CDF of xn. Also, let f star be the CDF. Then it is said that this sequence converges in distribution to f star if this one, right, is very similar. Okay, but instead, if we talk about the variables known, we talk about the CDF as a random variable here. Not random variable, is the variable here that will convert to f star x if n go to infinity. Okay, it's called the asymptotic distribution, and you will see this a lot in mathematical statistics. Okay, the delta method is that you have yn. Okay, you know the distribution of yn. You know the distribution of yn. But you want to find alpha yn. Actually, you could do something like what we have studied in chapter 3 and chapter 4 about finding the PDF. But if we talk about the asymptotic distribution, you can say that if alpha yn minus alpha theta times an divided by alpha, this is the first derivative at theta, it will convert in distribution to f star. It is the distribution that we already know. So we convert the distribution of the unknown into the asymptotic distribution of the known one. So that maybe sometimes if we, let's say, have yn normal, okay, and we have alpha yn, maybe it is difficult to, let's say what is that distribution. But if we convert into this form, we can say that it converts in distribution to f star. So in the intuition behind this, I think it is useful. Intuition is the first order approximation that we learn in the basic calculus, the linear approximation. That is, if you want to find alpha of yn around alpha of theta, you could say that this one, okay, this one. So I think it's good to draw some picture to show some illustration here. And we have the curve, something like this. Okay. So you know theta, you know alpha theta, right? But you want to approximate for what? For yn. Actually, if you could find the alpha of yn, is fine. But you could do some approximation. Approximation is drawing the linear approximation here. Okay, from the alpha theta. Okay, from the alpha theta, you want to figure out how far to go above to get this kind of approximation. How far above? So you have what? This is the distance, right? The distance is yn minus theta. And the slope, what? The slope is alpha prime of theta. So the distance, the height, okay, the height that we want to go is alpha prime theta times yn minus theta. That's the height that we want to go. That is the origin of the approximation. And the idea here is that if you want to convert to some familiar looking distribution, we just find what? We just find alpha yn minus alpha theta divided by alpha prime of theta. So it is approximately yn minus theta, right? If we know this distribution, so we can approximate this distribution using that distribution also. Okay, and that's the idea behind the intuition behind the delta method. Okay, and this is the special case of data. This is when we use the most. Okay, so let's see. Let's do some intuition here. Because what? Alpha xn bar minus alpha mu approximately equal to what? Alpha times theta. Okay, times theta is going to be what? Alpha times theta and is going to be xn bar minus mu. Okay, I think it's mu, right? It is mu, not theta. Sorry, it's mu. It's mu. I think I copied from the last slide. Okay, so it's something like this, and then we divide. Okay, we divide the alpha part mu to both sides, and then not only that, we are going to divide what? Divide by another term, sigma over square root n, and this is approximately, okay, equal to xn bar minus mu over sigma square root n, and this is what? Asymptotically normal. Normal 0, 1. So you could apply this and you can claim that it is approximately normal by using the delta method here. And this is the I think the use case of the delta method. Okay. So, and this is the end of the lecture 43. Okay. And see you in the coding section in the next